Okay, back to our second example problem of applying Newton's laws. Here we've got, again, essentially a one-dimensional problem. All the forces involved here for a person riding in an elevator are acting in the vertical direction. So 80-kilogram man in an elevator stands on a scale that reads in newtons. If the elevator is stopped, what does the scale read? And then the elevator is going to start moving in the other parts. And I should say, both the example problem we did before and this one only involve two types of forces. The weight force, which we talked about, you can use that formula mg, and contact forces that either were given, like that cable force in the previous problem, or that we want to know, like a scale force here. So the elevator stopped. What does the scale read? You might think that, well, if we want to know what the scale reads, we want to know what the forces are on the scale. But unfortunately, that's going to be kind of difficult to know because we don't know how much the scale weighs itself, and how much it weighs is going to affect how hard the floor of the elevator is pushing up on it. So rather than the scale reading, rather than focusing on the scale, let's focus on the man who's standing on the scale. And the idea is, here's the free body diagram. I've just drawn the man as a kind of a circle, labeled it with the man's mass because that'll help me remember what it represents. And the man has two forces acting on him as he stands there at rest. There's the weight force, mg, 80 times 9.8, going downward. And then there's a scale force going upwards. He's pushing down on the scale. The scale is therefore pushing up on him. So I wrote that as an unknown F scale. That's the force of the scale on the man. And now, in order to apply Newton's second law, we have to choose some axes. And in this case, all the forces are in the, just the vertical direction. So we could define what direction plus x was, but it's not really going to help us here. It will be important very shortly, but for this kind of problem, all that really matters is that we define what the y-axis, or you could call that the x-axis is, and you could choose up or down. It doesn't really matter. So let's apply Newton's second law along the y direction, or for y components. And again, Giancoli uses the notation of Greek capital sigma, that shape that kind of looks like a bent E, but that just means the sum of all the force y components. So that means the same thing as the net force. Net means add them all up. So the net force y components, according to Newton's second law, is going to be equal to the mass of the man times the acceleration of the man. And we don't see the man accelerating. The man's just sitting still. So AY is 0. So now it just remains for us to flesh out what the net force is. In other words, we've got two force y components that we have to add together to get the net force y components. Net force y components, well, the scale force comes in with a plus sign because, again, to go from the tail to the tip of the scale force vector, we're going in the plus y direction. So that force, this F scale, is just going to be the magnitude of the scale force. It's going to come in with a plus sign. So I don't have to put anything in front of it for a plus sign. And then the weight force is going to come in with a minus sign because in going from the tail to the tip, we're going in the negative y direction. And so that 80 times 9.8 gets a minus sign out in front of it because we're writing down y components of forces here. We have to pay attention to the signs. Okay, and we already decided that the right-hand side is equal to 0. So the sum of those two equals 0, and we can solve for the scale force. Now, technically what this means is we've solved for the force of the scale upward on the man. And that might sound a little bit confusing, but scales are calibrated to give the force that the object that is placed on them pushes down on the scale. But by Newton's third law, the force of the man down on the scale is equal and opposite to the force that the scale pushes upward with on the man. So we've found the force the scale pushes upward with on the man, and that's the same that that's the same force that the scale is calibrated to read if it's a correctly functioning scale. So that's what it reads when the elevator is not moving. B asks if the elevator is moving upward at 6 meters per second, what does the scale read? And so we could look at this free body diagram and the resulting F net equals ma and ask ourselves what changes in this situation. Well, just because the man is going up at 6 meters per second, that doesn't change what his weight is. He's still close to the surface of the Earth, and that mg applies no matter how you're moving. So that force is going to be the same. And I don't necessarily know that F scale is going to be the same, but there is some unknown F scale that I would like to solve for. And furthermore, AY is still 0, because if the man is moving upward at a constant speed, he's not accelerating, and therefore the sum of those two force Y components still has to add to 0, and that means the answer is the same. You have some experience with this where if you're in an elevator just standing there and the elevator's not moving, you feel normal. If the elevator's moving up at constant speed, once it's reached its cruising speed and is moving at a constant rate, you also feel normal, other than the vibration of the elevator, but you don't feel heavier or lighter than normal. So the scale reads what it normally reads as long as you're not accelerating. That all changes in C, where the elevator now is accelerating upward at 3 meters per second squared. And what we're asked, what does the scale read here? So again, the free body diagram isn't going to change. We can use the same free body diagram because even if you're accelerating, your weight is still mg, where g is 9.8, as long as you're close to the surface of the Earth. And there still is some sort of scale force pushing upward from the scale on the man, right? These are all forces that are acting on the man. So the free body diagram is exactly the same, and therefore the sum of the force Y components looks exactly the same. We don't know that that F scale is going to be the same number because the right-hand side is no longer 0, right? AY is not 0. Now we have M. When we do the sum of the forces, that's equal to m. That's always the mass of the object in the free body diagram. So here, that's 80 kilograms, times the y component of the acceleration. And the acceleration is up, plus y is up, so that's a plus 3 meters per second squared. Notice the answer we're going to solve for now is the previous one we got, 784, plus some extra amount added on to that, 80 times 3. So when we add those together, we get 1,024 newtons is the scale reading. And you may have some experience with this if you've ridden on fast elevators. You may notice if you're sitting still and the elevator is about to start going upward, there's a moment where it has to accelerate upward. And for a moment, when it first starts going, you do feel heavier. You feel like you actually have more weight. And that means the scale that you're standing on is going to read more. We've just calculated exactly how much more, 1,024 newtons versus 784. Finally, in D, the elevator cable breaks, unfortunately. I know I have sort of a morbid sense of making these problems, but hopefully no one got hurt in this problem. It breaks and the elevator falls freely. So we're in free fall right now, and the elevator's in free fall surrounding us, or the man is in free fall inside the free falling elevator. What does the scale read now? Well, most people have an intuition that it should read 0 because, it's just kind of like you're in outer space. You feel weightless. There shouldn't be any reason that you're pushing against the scale and it's pushing on you, but it would be nice if we could justify that with Newton's laws. So again, let's do the same free body diagram that we had before, right? Free body diagram looks like this. Even if I'm in free fall, the Earth is still pulling on me with my same weight. And I don't know what F scale is. Maybe it's 0, but I better put in something and solve for it. So the free body diagram hasn't changed. What's changed now is that I'm not accelerating up at 3 meters per second squared anymore. I'm accelerating downward at 9.8 meters per second squared if I'm in free fall. And so the change is that on the right-hand side, we have an 80 so this is F net over here, or the sum of the force Y components, is equal to m times AY, and AY is minus 9.8 if plus Y is up and we're accelerating downward in free fall. And notice now that this term cancels against this term, and the scale indeed should read 0 newtons. We didn't assume that. We still put in something for F scale, but we solved that it actually should read 0 newtons. Okay, so that's a good second example of a one-dimensional problem. Now we are going to move, so that was both those problems were essentially one-dimensional. Nothing was going on in the horizontal direction. Now we're going to step it up a little bit and go to a problem that is inherently two-dimensional. Here's an 8-kilogram box released from rest on a frictionless plane inclined at 25 degrees to the horizontal. Find the magnitude of the box's acceleration, and then I just threw a little extra kinematics problem in here. Once you know the acceleration, and assuming the acceleration is constant, we can find out something that we might ask in a kinematics context. How far does it move in the next 2 seconds? I gave you t, and I want to know x, if x is along the plane. All right, so the first thing I need to do is draw a little diagram. Here's the 8-kilogram box. It's sitting on a 25, I didn't do a good job of orienting this, but this should be absolutely horizontal, and this angle here is 25 degrees. And now I'm going to put axes next to this, and the temptation of almost everyone, if they've never done this kind of thing before, is, well, why not put in your axes horizontal and vertical? It seems like it would make sense because the weight of the box is still going to be downward in the vertical direction towards Earth. So why not try this? The answer is you can try it, and you'll find out that things go a little bit haywire. And that is the reason that choosing horizontal and vertical axes like this is a bad idea when you're looking at a box on an inclined plane, is because we know that the subsequent motion is going to be along the direction of the plane. This plane has no friction, so it's like a box that's sliding on ice or something like that, very low friction. And so if we release it from rest, it's going to start accelerating in that direction. Notice the acceleration vector is neither along x nor along y. So if I want to know the magnitude of the acceleration, technically I would have to find ax and separately ay, and then take the square root of the sum of the squares to find the magnitude of the acceleration. And that's just making extra work for me. So in this case, let's just try it, and you'll find that this is usually a better idea when you have an inclined plane problem like this. Instead, let's take one of the axes, I'm going to call it x, aligned along the direction of the plane, which is along the direction of the known acceleration, and the other one perpendicular to the known acceleration. And that way, with those axes, I automatically know that ay is going to be 0. I don't have to worry about solving for ay. If I can figure out what ax is, then that is going to be the acceleration magnitude. And generally, the principle we're going to use to choose the orientation of the axes that always works for everything we're going to do in Physics 110. To simplify your life, always choose, if you know the direction that something is going to be accelerating, choose one of your axes to be aligned with the acceleration vector. And that way you know the component of the acceleration vector along the perpendicular direction is 0. So in this case, we know ay equals 0. And we're going to use that to our advantage to make the algebra much simpler. We don't want 2 equations in 2 unknowns. We'd rather have just one equation in one unknown. Okay, here's what the free body diagram now looks like. I guess I should talk a little bit about what frictionless means. We'll talk about friction in more detail at the end of the chapter, but when something is frictionless, what that means is, we talked about the poor fellow pushing the box along the plane and friction was pushing back. When friction acts as you're sliding something along a surface, it's a force that's directed along it's directed parallel to the surface that the thing is sliding on, and it always acts opposite to the motion of the object. So if a box is sliding to the west, friction acts to the east, right? It always retards the motion or tries to push back against it. So what that means for this plane is that if this plane is frictionless, the plane is incapable of pushing with a force on the box that's along the direction of the plane. If it were pushing on the box along the direction of the plane, it would be acting like friction. And so in this case, if there's no friction, the only way that the plane can push on the box is in the direction perpendicular to the plane. In other words, the plane's got to push on the box. If the plane weren't pushing on the box at all, the box would just free fall straight downward. It doesn't do that, and the reason it doesn't do that is because there's a force acting perpendicular to the plane direction. Even though there's no friction, it can still push in the direction exactly perpendicular to the motion. So we've got the weight force going straight down in my free body diagram. I'm drawing a free body diagram for the box. There's not really a lot of choices for other things to do it for here, so it's pretty clear. The weight force is 8 times 9.8 and directed downward on the box. Doesn't matter if it's on a plane, still acts straight down towards the center of Earth. And then we've got another force from the plane on the box, and we might have labeled it as F plane on box, but here I've just labeled it as N, and that stands for a normal force. Normal means perpendicular in this context, and the force is directed perpendicular to the surface that the box is sliding on. And you can look around and try to see, are there any other forces, but there aren't. Without friction, there are no other forces that seem like they're acting here. And so I'm going to take my own advice and attach some axes to the free body diagram, where one of them is parallel to the direction it's accelerating and the other one's perpendicular. I'm going to call those X and Y. Just for my own convenience also, I have labeled this angle in here as 25 degrees. Notice that I didn't do a good job of drawing this over here, but if I draw that direction straight down, when I draw that direction straight down, I'm making a little right triangle right here that has a vertical side right there. If that angle is 25 degrees to the left, then this little angle up here is 90 minus 25 degrees. And so that would be this angle right here is 90 minus 25 degrees. And since these two angles add up to 90 degrees, this angle here should be 90 minus 25, which is just 25 degrees again. In this case, the 25-degree angle can also, usually a good way to reason about it is to say, I can kind of see that if I made this plane close down to a very small angle, so I imagine the plane going to smaller and smaller angles so that this plane becomes almost horizontal. In that case, this dashed line I have right here would get closer and closer to the vertical direction. And since when this angle closes up, this one also closes up, that's a very strong hint that those are actually the same angle in this context. So if that helps you do a little shortcut argument to figure out what that angle is, we're going to find it's always very useful to draw in this angle. And when you're on an inclined plane, that angle is going to be the same as the angle of the inclined plane above the horizontal. All right, so let's now apply F net equals ma components. We're really interested in the magnitude of the acceleration. That's the first thing that's asked, and that's going to come into the x component equation, right? We want ax. We already know ay is 0, so we really only need to solve for ax, and let's use the equation where it's going to come in. The sum of the force x components is equal to max. All right, this force, the normal force, has 0 x component, right? Because in going from tail up to tip, I don't have to move along the x direction at all. It's exactly perpendicular to it. So this one has 0 x component. I didn't even write that one in there. And then I also need the x component of this force. And this one does have an x component. In other words, in going from the tail to the tip, if I go, say, first along y and then only along x, it's the going along x distance that I want. And when I go along x, I'm going in the positive x direction according to my axes. So this is going to be a positive x component to the force. So what I want to do is find the magnitude of the length of this side in the right triangle that I've got drawn there. So that would be, well, let's see. The hypotenuse has length 8 times 9.8. I'm going across the angle that I'm given in the right triangle or that I have drawn in. I don't like going across angles, and I don't like the sine for no good reason. And therefore, what do I do to that 8 times 9.8 to get to this side? I multiply by the sine of 25 degrees. So 8 times 9.8 newtons. That's not the variable n, that is the symbol for newtons that I mean there, times the sine of 25 degrees. There were only two forces, but only one of them had a non-zero x component. So there's only one force that's coming into this, this sum of the force expression here. And that's equal to the mass of the item in the free body diagram. That's 8 kilograms. I usually draw the mass into my free body diagram so it's clear what I'm talking about, times the unknown AX. And now I can just solve for AX. So what I want you to do now is continue solving for AX, put that in your calculator, and then try to use your kinematic skills to solve this second question there. How far it moves in the next 2 seconds if it's released from rest on that frictionless plane. Okay, we'll be back with that in a moment.